All right, we're continuing our conversation with random variables. Today we're going to be talking specifically about binomial random variables, and later on in this chapter we'll be getting to talk about geometric random variables. But both of these are examples of discrete random variables specifically, and they hold all the properties of discrete random variables, but they also have some of their own properties as well that we'll understand as we go through. Some of the objectives that we're focusing on here. What are the conditions that it takes to have a discrete random variable be binomial? How can we find the probabilities and how can we interpret those probabilities for binomial distributions? How can we calculate the mean and standard deviation of a binomial distribution? And talk about geometric distributions as well and how they are similar but yet different than the binomial random variables. And we'll also talk a little bit about normal approximation, although it's not something that you are required to know for the AP exam. So a binomial setting. So we know what discrete random variable means. Discrete random variable means we have a countable number of outcomes. But when we are talking about a binomial discrete random variable, we have a few extra conditions that go into it. First, the outcomes can be categorized into either a success or a failure. So if we use a free throw shooting example from basketball, you either made the shot or you missed the shot. But it doesn't mean that it can only have two outcomes. It just means you can categorize the outcomes into successes and failures. For instance, if I'm talking about rolling a die, I could say rolling a 1 is a success. Everything else is a failure. So we have one success, but there's 5 outcomes that represent a failure. The next condition you need to have for a setting to be binomial would be independence. And basically, as we know, that means that the outcome of one trial has no impact on the outcome of another trial. The number of observations that we have has to be fixed in order to be a binomial setting. So if we're shooting free throws, we shoot 20 free throws. You don't shoot until something else happens. We shoot exactly 20. If we're rolling a die, we roll the die 10 times, and that's it. It has to be a fixed number there. It can't vary. And the last condition is that the probability of success must remain constant. So these are the 4 conditions for a random variable to be a binomial random variable. You can remember it using the acronym BINS, B for binary, success or failure, I for independence, N for number, a fixed number of observations, and S, that the probability of success remains constant. If we consider tossing a coin, now tossing a coin isn't inherently binomial until we really talk about what it is that we're looking for. Now, if we toss a coin n times, and we're looking for the random variable x, which represents the number of heads, well, now we have something that is going to be a binomial random variable, because we are saying we have a success, that's getting a heads. We have independence because one flip of a coin has nothing to do with the outcome of the next flip of the coin. We have n observations that we're observing, and the probability of success obviously is always going to be 0.5. Now, when we talk about these binomial random variables, we want to make sure we understand the distribution of them. And when we talk about the distribution, it's kind of like when we talked about normal distributions. When we did normal distributions, we had these parameters, these things that we needed to know about the normal distribution so that we could use it to find probabilities. For a normal distribution, those parameters were the mean, mu, and the standard deviation, sigma. When we're talking about a binomial distribution, we still have 2 parameters, but those parameters are n and p. N is the number of observations we observe, and p is the probability of success. Now, when we talk about the random variable x, we're talking about how many successes we do have. And specifically, we're going to say that we could have anywhere from 0 to n successes. So understanding that phrase binomial distribution, what it means and how you state it is important moving forward. So let's look at this example here. It says each child of a particular pair of parents has a probability of 0.25 of having blood type O. Genetics says that children receive genes from each of their parents independently. If these parents have 5 children, we could refer to the count X of children with type O blood as a binomial random variable, with n equals 5 because there's 5 children, and the probability of success being 0.25. And obviously that's going to be constant for each trial. In this setting, a child with type O blood is considered a success. We'll call that S. And if they do not have blood type O, we'll consider that a failure, and we'll refer to that as F. Now the question, now that we've identified this as a binomial random variable, the question is, what's the probability that X equals 2? Meaning, what's the probability that 2 of the 5 children have blood type O? Well, I could look at it like this and say, okay, the probability of SSFFF, where the first 2 children are blood type O and the 3 following are not. And since they're independent, we can multiply those probabilities out and get 0.02637. In other words, about 2.5% of the time. Well, that's great, except we need to understand that there are other ways that we could organize these successes. What if instead of the oldest 2 or the youngest 2, or the oldest and the youngest, or 2 in the middle? We need to think about all possible ways that we could arrange these successes. As we see right here, those 2 successes can be organized 10 different ways. And each one of them has a probability of success of about 2.5%. So if we wanted the overall probability that X equals 2, we could just take that 2.637% and multiply it by 10 to get about 0.2637, or about 26.37% of the time. Now with this one, it wasn't so bad because I could write out those 10 different arrangements. But obviously, we don't want to have to do that every time. And that's where the binomial coefficient comes in. We could think about how many different ways we could organize this, and we can use something that you learned back in Algebra 2. We could use the combination method. It says, in a previous example, any one of the arrangements of 2 S's and 3 F's have the same probability. And obviously, we know that because we're just rearranging the way we multiply there. But if we're trying to find K successes in N trials, we would look for N choose K. Now, N choose K, the formula from Algebra 2, can be found by using N factorial divided by K factorial times N minus K factorial. And we can do that, but obviously that's going to take a little bit more time than we'd like to, so we'd most likely be using our calculator to get this, using the NCR function in the math probability menu. So if we look at that and we can find the binomial coefficient, that's the number of ways that we can arrange the K successes. And then once we have N choose K, then we can multiply that times P to the K as 1 minus P to the N minus K. And this formula, as you see in the yellow box in the middle, is how we find our binomial probabilities. Now the good news is this formula is on your formula sheet if you need to know how to use it. So let's take a moment and make sure we understand each and every part. The first part here, the N choose K. Not N divided by K, there's no division points. N choose K is how we read it. And this is the binomial coefficient. And it is the number of arrangements of K successes in N trials. When we talk about P to K, that's the probability of K successes. So whatever the P is, you raise it to the number of successes that you're asking for in this particular question. And then the 1 minus P to the N minus K, that's the probability of N minus K failures. If P is the probability of success, then 1 minus P is the probability of failure. If you have K successes, then you have N minus K failures. So it just makes sense when we plug into the formula. Now, if we're looking for binomial probabilities, the first thing we want to make sure we do is we understand what the distribution is. You want to make sure that you state that it is a binomial distribution and state the parameters being number of trials N and probability of success P. And then you can go ahead and perform the calculations. You can use the binomial probability formula that we just saw in the previous slide, or we could use the binom PDF or binom CDF commands in your graphing calculators. These are things that we'll practice in class. Both of them are pretty easy to use, but use them in different circumstances. If you're looking for the probability of exactly K successes, then use binom PDF. So you're looking for the probability that X equals 3 for the previous example, use binom PDF. If you're looking for a range of values, you use binom CDF. But again, we'll talk about that in class. And then obviously you answer the question in the context of the problem. So we would say about 26% of the time, we would have 2 children with blood type O. Let's look at another example using a similar setup. It says each child of a particular pair of parents has a probability of 0.25 of having blood type O. suppose the parents have 5 children. If we wanted the probability of exactly 3 children having blood type O, we can go ahead and establish that it's a binomial distribution with n equals 5 and p equals 0.25. And then we can choose whether we're using the formula or the calculator. We'll focus here on the formula. We're going to say 5 choose 3 times 0.25 to the third times 0.75 to the second. You'll notice that 5 choose 3 ends up being 10. There's 10 different ways you could organize those 3 successes. And that ends up being 0.08789. Or in other words, almost 9% of the time will you have 3 children with a blood type O. And again, we could have done this using binomial PDF by entering in 5 for n, 0.25 for p, and 3 for x. If you're wondering where binomial PDF and binomial CDF are, they're in the same second bars menu that the normal CDF and the inverse norm are. Let's look at question B. It says, should the parents be surprised if more than 3 of their children have blood type O? To answer this, we need to find the answer to probably that x is greater than 3. Well, if x is greater than 3, it could be 4 or it could be 5. So we're going to use this same formula, or we're going to use it to find probably that x equals 4 and x equals 5, and add those probabilities because they are disjoint. When we do so, we see that those probabilities are very small. Even when you add them, they're less than 2%. So should you be surprised? Yeah, you should be surprised because it's going to happen less than 2% of the time. All right? So that's it for this introduction to binomial probabilities. In class, we'll talk about it some more and do some more examples and talk about how to use the graphing calculator to help us out with these problems here. Have a good day.